What makes quantum computers fastest of all, even faster than supercomputers? Let's explore. Hi there everyone, welcome to my channel. And here is the demo. Let's first look into the classical or the digital code or digital demo. Then we'll look into the equivalent of a Qiskit or quantum demo. So the objective here is to iterate through a randomized list of size say 16, and the randomized list contains all the numbers, all the possible numbers between 0 to 16, which is 2 to the power of 4. In the best case scenario, it would take one iteration for you to walk through the entire list. But in worst case scenario, however, you have to walk through all 16 elements to figure out a number that you are interested in. For example, if I'm interested in a number 12 in a randomized list, it would take either one iteration or 16 iterations to cherry pick the number. And the computational time complexity of this code is big O(n), and generally this is the notation, big O notation, big O(n). And the code is almost self-explanatory. So have the list here, a list. Apparently it is just it's a list of 16 numbers 0 to 1, and here I'm randomizing or shuffling the list, and this way I'm not sure where exactly this 12 is located. I don't know, if I can actually make 11 iterations to get this list or so. So I'm randomizing the list, and through the for loop, using the for loop, I'm iterating through the list to cherry pick number 12. And let me simply demo. All right, so here we go. So I'm deliberately introducing a delay of 2 seconds only for demonstration purpose, but this is not the real case, of course. So assuming that our computer is a supercomputer, super duper computer, in fact, it's taking almost 24 seconds, 26 seconds. That's interesting. 28 seconds. Okay, it took at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 iterations. 16 iterations to for loop to go through and cherry pick this number 12. And this is how typically a traditional microprocessors work. Of course, supercomputers are capable of doing the parallel processing, where you won't need this many iterations. You don't need to go through this many iterations. However, supercomputers do have certain limits that quantum computers excel. That's the domain where quantum computers excel. So without further ado, let me show you the quantum code. And now let me show you the quantum code. Here the objective is the same. Again, we are kind of iterating through a randomized list of 16 numbers, but in a quantum way. And here is the Qiskit demo, which is a quantum demo essentially. So to start with, I'm importing all necessary libraries, and I defined libraries in this IPython notebook, and here is the reference. So from Qiskit, I'm importing quantum registers, classical registers, quantum circuit, and transpile. And within the Qiskit demo, again, within the Qiskit framework, I'm importing quantum info, and from quantum info, I'm importing state vectors, density matrix, and also operators. Operators is where you define a custom gate or custom operation, a unitary operation essentially. And from quantum visualization, I'm importing the block sphere followed by a plot histogram. I'm also importing the AER simulator from Qiskit AER, also importing numpys. And now this little unitary operation. So here I defined two functions. One is do nothing, which essentially returns an identity matrix of 2 to the power of number of qubits in this case. So in this case, it's 4. So that is a 16 by 16 identity matrix is written when we run this do nothing operation. And also a CC NOT gate, which is a controlled C NOT gate. And this is the matrix corresponding to the controlled C NOT gate. And the same matrix is being written in the form of an operation. So moving on to the main code. So here I'm defining the number of qubits, in this case 4. I'm just dealing with 4 qubits for this demo purpose. And here I'm defining the qubit sequence. Qubit sequence is essentially a small list of numbers starting from 0, 1, 2, 3. So this represents my 0th qubit. This should represent my first qubit, second and third. So Qiskit follows the little endian notation. So the right hand side is the most significant qubit, and the left hand side is the least significant qubit. That's Qiskit's notation. Though I prefer big endian notation. Alright, let's define a quantum register here. Quantum register is nothing but a collection of qubits, and here we have 4 qubits. So I'm passing number of qubits as my argument, followed by a label. All the states are prepared in ket0 state. That's where this notation comes from. So ket0 followed by qreg is the symbol. And now we'll define the classical register. Like quantum register, classical register takes 2 parameters, 2 arguments, number of qubits followed by a label. And now quantum circuit. Quantum circuit is it's nothing but it's a collection of labels and operations and also measurements. So it takes 2 arguments. One is quantum registers followed by a classical register, and this is the notation here. By default, Qiskit initializes all qubits into state 0. To validate, I am using the state vector function here. So the state vector function takes circuit as its argument, and it returns the current status of the state of the quantum circuit. And to print, I am using the draw function and printing output in the form of latex. You see here, this is the Dirac representation, Dirac ket notation of 0th state, or ket 0, 0, 0. Since there are 4 qubits, you see 4 zeros here, obviously. So our qubits are all good now. So they are in the state 0, 0, 0, or initialized into ket 0, 0, 0 state. So we have prepared our qubits into ket 0, 0, 0 state. But forever this is 0, which is of no use to us. Then how can we achieve the list of having all 16 numbers, 0 to 16? That's where we use the phenomenon called quantum parallelism. To achieve that, we use the Hadamard gate here, or the superposition gate here. Now I'm applying the superposition gate on all the 4 qubits using this code. So to the quantum circuit, I have to apply on each qubit a Hadamard operation. So this is the Hadamard operation, or superposition operation. And let me show you the circuit now. There we go. So these are the initialized qubits into state 0. All states are being initialized into 0, obviously. And here I'm applying the Hadamard gate. All these H gates are Hadamard gates, and here is the classical register. Now let me undo it. And now let me show you the state. Boom, here we have all the 16 states, or let's say all the 16 numbers simultaneously being spun here. You see 0, this is 1, this is 2, this is 3, this is 4, up to this is 15. So we have all the 16 numbers available for us through this mechanism of quantum parallelism, which is only possible with quantum computers. Now this is a superposition state. We have all the states available in the form of wave function. But our objective is to cherry pick one of these superposition states, one of these states, not exactly all. So we need to cherry pick the 12th number, or let's say this state. So to achieve that, we have to do certain operation and finally collapse all the other wave functions like get 0 0 onwards to get 1 0 1 1, except this one followed with others. All these states, we must all collapse all these states, but we have to have this state alone available for us. So we can do multiple operations. So in this case, in this specific demo, I am using the Z operation or Z gate on ket 0 and ket 1 to achieve that. So let me show you the code again, or let me show this circuit. Yes. So here is my ket 0 0 0 state. So the initial state prepared here. Now I am applying the superposition operator here, or to achieve the quantum parallelism. And now I am applying the Z gates on first qubit or 0th qubit and the first qubit. And now let me show you the output of this operation, or let's say the wave function. Okay, I do have it here. MPL. I use this MPL for a better picture. Okay, let me move this up. Oops, this. Oh, sorry, I think it's sorry. Okay, let me rewrite the here we go. So the fundamental difference is that this phase we have now we have applied the phase. If we assume this as a wave function or a broader wave function, and here these are the local wave functions. So our larger wave function is a Kronecker product of all these smaller wave functions of individual qubits, and here we see the local phase being applied here with the help of Z gates, and this becomes our distinguisher in order to isolate the wave function we are looking from the global wave function. Now this entire basis, or let's say this entire wave function, is in Hadamard basis. To achieve the objective, or to obtain the output, we must convert this entire wave function into a Z basis. To convert, we apply Hadamard operation again. Remember, Hadamard operation is always unitary. So applying Hadamard twice or even number of times end up with as good as performing no operation. So I'm applying a Hadamard operation on all 4 qubits. So here is the circuit. So, and here is the code. This is the circuit. Applied Hadamard operation to achieve the quantum parallelism. Then applied the filter, or let's say then applied the algorithm, true oracle or true algorithm here to obtain the number I'm looking for. In this case, I'm looking for 12. Therefore, I applied Z gate here. You can apply any other algorithm depending upon your choice. And again, I'm applying the Hadamard operation to perform the measurements in Z basis. And here comes my output. So Qiskit uses little endian notation, as I said in the beginning. Let me endian, where the most significant bit is on the right hand side towards this ket symbol, this angular bracket, and the least significant bit is on the left hand side, which is the line or pipe symbol here. So this is 1100, which is digital equivalent of 12. So the whole global wave function is being collapsed into a single wave function by using certain operations. And now we will perform the measurements. So the measurement is performed with this operation. So from quantum all qubits to classical bits. So the objective here is to convert this collapsed wave function into a binary equivalent of number. For example, this is 0011, a quantum expert reads this as 12, but to transmit or to translate it into a classical or digital value, we must do the measurement here. So so we use this on the quantum circuit. I apply measurement from individual qubits. So get one from 0 to 0. So this is 1-to-1 correspondence here. So 0 to 0, 1 to 1, 2 to 2, and likewise. So these are the measurements, and this is a circuit representation of a measurement here. And now we'll print the output. So okay, I think for the time being you can ignore all these wave functions. Now let's go back to the simulator. Now the circuit is an abstraction. All this is abstraction. To make that abstraction into a reality, we need simulator. So we use the simulator here. So this is the method for simulator. So first of all, I initialize the state simulator, and then I transpile using the simulator and create a transpiled circuit. And then I run the circuit for shots 1024 to obtain the results. And here is the probability, or let's say the output measurements. You see here, so I obtained the maximum probability at 12, 1, 1, 0, 0. So here it took total n number of iterations, or let's say the worst case scenario is actually 12 in this case, whereas in this entire quantum effort, our order, or let's say the big O, or time complexity, is just 1. Whereas in a classical case, we ended up with ON, which is a worst case scenario. That is, at least we have to do 16 operations or 16 iterations to obtain 12. In quantum case, however, it is just in one iteration. This is called the quantum advantage, often called quantum advantage. I'll stop here in the interest of time. Hope you guys enjoyed it. If you could, please comment, like, share, subscribe. Thanks. Until next time.